Okay, so let's start from where we stopped yesterday, which was talking about underactuation and contacts. So what we saw so far was how to control a robot that is fully actuated using a least square program. And that optimization problem can be cast under the following form. So we want to minimize with respect to this variable z, which contains the joint accelerations and the joint torques. We have a least square cost function, which we saw how it can be formulated. And we saw the three cases. You can have a cost that is a function of the control inputs, u, or that is a function of the joint configurations, q, and then you need to take the derivative twice to get something that is a linear function of the joint accelerations. Or you can start from a cost that is a function of the joint velocities, and you take the derivative once, so you get something that is, again, a linear function of the joint accelerations. And then the constraints are simply the dynamics of the system. Okay, so that's what we saw yesterday. How do you deal with the case when the robot is not fully actuated? Because we know that legged robots are underactuated systems. Well, the extension is almost trivial. We simply replace here the identity matrix with the selection matrix S transpose, which was the selection matrix we introduced yesterday when we saw the model of legged robots. So this is a matrix that contains zeros in the top part and the identity in the bottom part, and simply augments the torque vector with a bunch of zeros in the top elements. So it's very simple. You just substitute this matrix, and now your dynamics of the system considers the underactuation. So that's the beauty of optimization-based control, that with a very simple change, you can generalize the framework to a much larger class of systems, because now with this, we can take into account legged robots, wheeled robots, flying robots, and underwater robots. Of course, this selection matrix is going to be different depending on which kind of robots you're going to use. The one we saw yesterday was the one for legged robots, but it's not very different also for the other systems. Okay, let's now talk about contacts, because we also know that legged robots are typically in contact with the environment, unless you're in a jumping phase, but that's quite rare. So we need, first of all, to account for contact forces. And if we assume that the contacts the robots are making are soft, so like coming in contact with an elastic environment, then we can estimate the contact forces somehow. We get this value f hat. So this could come from the measurement of a force sensor, or it could come from a model that we have of the contact. So we are able to estimate the contact force based on the position of the contact points. No matter which method we use, if we have an estimated contact force, we can simply add that contact force inside the dynamics of the system. So we get this J transpose F hat, and the framework remains the same. However, this case is not very interesting in practice, because most of the times contacts are not soft, especially for locomotion, unless you're jumping on an elastic mat, but that's not what we're going to do. So we are. Guess who's there? Most of the times contacts are rigid, and we know that rigid contacts are a bit more complicated because they constrain the motion. So we already saw how this goes. We can represent the motion constraint with this equality, saying that the position of the contact points is constant. But then we cannot include this directly inside the problem, because this depends on the joint positions. We need something that depends on the joint accelerations. So we take the derivatives twice, and we get this constraint here, jv dot plus j dot v equals 0, which means the contact point accelerations is 0. And then we introduce this constraint in the problem formulation. So now the dynamics has two parts. One part, which is the usual multi-body dynamics, which is the bottom row, and one part which just says the contact point shouldn't move, and that's the top row. And another thing we had to do in this case was to introduce the contact forces as an optimization variable. This is because now, under the assumption of rigid contact, the contact forces are a direct consequence of the joint torques that I'm applying through the motors. That's very different from the case of soft contacts. In the case of soft contacts, the contact forces are a function of the state of the robot, because typically they depend on how much I am penetrating in this soft material. The more I'm penetrating, the more force I get in return. If the contact is rigid, there is no penetration. And so the contact force is only a consequence of how much am I pushing against the surface. So if I'm pushing strong, I'm getting a high force in return. If I'm pushing very lightly, I'm getting a light force in return. So in this case, the contact force cannot be estimated beforehand, but it must be computed together with the decision of which joint torques am I gonna generate through my motors. Okay. So as we already said yesterday, the main benefit of switching from like analytical based formulations to optimization based is that we can introduce inequality constraints. So now our optimization variables are extended with respect to yesterday because we also have the contact forces. And we can add any constraint that is linear in these optimization variables. So we can have the joint torque bounds, the joint acceleration bounds, as we saw yesterday, but we can also have linear constraints on the contact forces. And those are going to be very useful to represent things like such as the friction cones, because we want contact forces typically to remain inside the friction cone. Otherwise, we might have slippage, and you typically don't want your robot to slip while it's walking. Yeah, so there is, I thought there was some more information on that. So the friction cone constraints are quadratic constraints because you have a quadratic cone. So if you look at the cone from above, you're going to see a circle. You imagine cutting this cone. So this cone would be something like that. If you see it from the side, imagine this is the ground, and your contact force must remain inside this friction cone. The angle of this cone depends on the friction properties of the material that are in contact. So if you have rubber against rubber, you're going to have a high friction, maybe 1. If you have metal on metal, you're going to have a lower friction, maybe something like 0.2. So it really depends on the material. And if you look at this cone from above, you're going to see a circle. So the problem is that we cannot include that directly inside the optimization, because that would be a quadratic constraint, which we can also write down. It would be the norm of the tangential force, Ft, square should be less than or equal mu times the normal force square, where mu is the friction coefficient. And the Ft is the tangential force. Which is two-dimensional. and Fn is the normal force, which is just a scalar. So since we cannot include this directly inside the problem formulation because that's quadratic, what we do typically is that we take a conservative linear approximation of this cone, something that's gonna look like that when you look at it from above. So you get a polygonal pyramid, and depending on how many sides this pyramid has, you're gonna be more or less accurate. So in this case that I've drawn here, I took 4 sides, so that's not gonna be very accurate. If you want to be more accurate, you can take 8 sides like that. And typically people take from 4 to 8 sides. I've never seen more, and then I've never seen less, because less than 4 it becomes a very poor approximation, and typically more than 8 is not needed, because already with 8 you have, I don't know exactly the percentage, but it feels like you have more than 90% of the coverage of the shape. So when you write this pyramidal friction constraints, you get a linear inequality of this for BF less than or equal to 0. We could also include things such as collision avoidance constraints to avoid colliding against the environment, objects, whatever. But these are a bit more complicated because they suffer from the same problem we discussed yesterday related to joint position constraints. So if you write them naively, simply saying that you don't want to be in collision at the next time step, the effect you get is that the robot can go very fast towards an obstacle, and then it's just gonna try to stop when it is super close to it. And that typically doesn't work because you don't have enough torque to decelerate so fast. And so to make this work, you need to go through some methods that are similar to the ones in the paper that I was mentioning yesterday. So you need to figure out that you need to decelerate in advance, but figuring out exactly how much in advance you need to decelerate, that's not trivial. And actually, John is working on these kind of problems. So if you have questions, he knows. Okay, let's briefly talk about multitask control, because so far we have assumed the robot has to do one thing only at a time. So when you're working with legged robots, especially if they're humanoids, these are very redundant robots because they have lots of degrees of freedom, and typically with respect to the tasks they are performing, the number of degrees of freedom they have is much, much larger. So a humanoid has something between 30 to 50 degrees of freedom typically. And if we think about the task of walking, so walking is mainly concerning the position of the feet and the position of the center of mass of the robot. So mainly your upper body is completely redundant with respect to the task of walking. Indeed, you could also walk without arms or without a head. You don't need those degrees of freedom for walking. There are walking robots that are just a pair of legs without anything above, and they walk just fine. Actually, they walk better than the ones with an upper body because it's easier. You don't have the weight of the upper body to carry around. So these robots are redundant with respect to the task they perform. Well, even 7 degrees of freedom manipulators are redundant because typically you care about position and orientation of the end effector, which has 6 degrees of freedom. So you have 1 extra degree of freedom, which you might decide to use for something else. A biped, for instance, if you take a very simple biped, so just 2 legs, you have 18 degrees of freedom because you have 6 for each leg, plus 6 for the base, which is this the extra degree of freedom that we discussed yesterday. We need to add to represent the pose and the orientation of the robot in the environment. And if you want to control just the 2 feet, you have 12 degrees of freedom as a task. So you have 6 extra degrees of freedom. So the idea is we can use the redundancy to execute secondary tasks. And let's define how we're going to represent this task. We can encode task using these least square functions. We're going to call GI of y. Actually, here it should be z because we said that the variable is z, but forgive me for this. Now the variable of the problem are y. So we have this GI of y, which is a least square function of y. And we have n of these functions. Each one represents one task that we want to achieve. So one possible way to combine in this task is to simply sum them all using some weights. Okay, so now our cost function is going to be the summation of these least square functions, each one multiplied by a fixed weight, which is user defined. So the good news is that if you're summing up least square functions, what you're getting is a least square functions. So it doesn't change the form of the function. You can always represent that as a single least square function. And the main advantage of this approach is that it is computationally efficient because the problem hasn't changed form. So you have always a least square program, so it takes the same time to solve this for one task as it takes to solve this for 10 tasks. Doesn't change anything. Well, you need to compute, of course, these extra task functions, but typically that's very fast. The time for solving the problem remains the same. The problem is that you need to figure out a correct set of weights to use here. So these weights are going to represent how much you care about a certain task. If you care a lot about a certain task, it's a high priority task. You're going to assign a high weight to it. If it's something instead that you don't care much about, it's mainly there for regularization purposes, you're going to assign to it a very small weight. Typically, these weights are going to differ in terms of order of magnitude. So you're going to have something like 10 to the minus 3 for the low priority task, 1 for the average priority task, and 10 to the power of 3 for the high priority task, something like that. We're going to see some examples when we move to the coding part. And since you need to use weights that are typically very different in terms of magnitude, one from the other, you might end up with mixing weights that are very large with weights that are very small. And if you do that too much, so you start having 10 to the power of 9 and 10 to the power of minus 9, then things are not going to work well. Because basically you end up with a Hessian matrix for this problem, which is very ill-conditioned. So this Hessian is going to have eigenvalues that are very large and eigenvalues that are very small. And that's by definition an ill-conditioned matrix. An ill-conditioned matrix are not going to make your solver work well, because then to do numerical decompositions of these matrices, the algorithms don't work well because we have a finite precision arithmetic on a machine. So you need to be careful when you're doing this approach not to use weights that are too large with weights that are too small. So in my experience, if you limit yourself in a range of 10 to the power of 6 between the largest and the smallest, you're fine. If you start going above 10 to the power of 9, then you might get troubled. So you typically get to very large ranges, like 10 to the power of 9 or above, when you have many tasks, and you want basically strict priorities between these tasks. So you want that task 1 is almost infinitely more important than task 2, and task 2 is almost infinitely more important than task 3, and so on and so forth for like at least 4 or 5 tasks. So if you are in that situation, then you might be better off using another approach, which is the strict prioritization approach, or also known as hierarchical multi-objective optimization. So in this case, you don't need to assign weights to the task. You just assign priority levels, which are like integer values. And you say that task 1 is more important than task 2 is more important than task 3, and so on and so forth. So you have just an order between the tasks. You don't assign weights. After you have assigned this order between the tasks, what you can do is that you can solve a cascade of n least square programs. In the first program, you're going to minimize the first task function, so G1, subject to the usual dynamic constraints. And then when you solve the second problem, you're going to minimize only the second task function, so G2, subject to the constraints that G1 should be equal to the optimal value that you found solving the previous problem. And you keep going like that. So you solve one optimization problem for each task where you minimize only one task function, subject to the constraints that the task functions of all the previous problems remain unchanged in value. Okay. So, and these are the priority tasks, priority constraints. So there are the constraints that ensure that the priorities are not violated. And if you think for a moment about this, it should make quite a lot of sense that what you're doing is basically ensuring that you have a strict prioritization between the tasks. So this behavior is the limit case of the weighted approach when the ratio between the weights goes to infinity, which of course you cannot do because of the problems I told you about before. So the conditioning of the Hessian matrix. So if you want to have a large range of weights that is too large to work on a real machine, then you need to switch to this strict prioritization approach. The pros and cons, I think, are quite obvious. The pros is that here it's easier to define the priorities because typically you know which task is more important than the other. And that's easier than finding the weights. For the weights, you have infinitely many options. Here you have a finite number of options to choose from. And the cons is that here you're not solving just one least square program, you're solving n least square programs. And even if solving one least square program is pretty fast, if you need to solve 5 of them, 6 of them inside a control loop, there it becomes a challenge because they're not so fast that you can solve 5 or 6 of them in 1 millisecond typically. So people have done this in practice and they've implemented that on real humanoid robots, but they had really to push the amount of effort in the implementation to the limit to make this super efficient. There are ways of making this super efficient. Theoretically, it could become even more efficient than the weighted approach. It's not intuitive at all to me, but it is possible. And actually, Nicolas Mansart, which some of you know, was one of the main people leading this effort to show that you can solve the hierarchy of least square programs faster than you can solve the single one with the weighted approach. They were able to prove that also empirically. But the problem is that there is no available solver that is mature enough to be used in practice to solve this kind of cascaded approach. Okay. So in practice, what we're going to do is that we are not going to use this, even though the library we are using as an API, as an interface that allows for formulating problems in this form. So the API allows it, but the implementation doesn't. It's my fault. I was the designer of that library and that API. And the idea was that eventually one day, if we wanted to, we could implement also that feature and the API wouldn't need to be changed for that. But now I'm sitting here 6 years after the design of that library, and that day has never come. So I suspect it might never come in the future. Well, hindsight is 2020. That's how they say it in English. So let's talk about computational aspects. So TSID, which is this framework I've just described of using least square programs to do reactive control, solve this least square program at each loop. So what we are doing is embedded optimization, which is very similar in spirit to model predictive control, which you might be more familiar with. We have a limited computation time, typically ranging between 1 and 10 milliseconds. So let's think a bit about the size of the problems that we need to solve. So let's imagine we have a robot with NV degrees of freedom. So that's the number of joints, basically, of the robots. NVA motors. So actually, NVA is the number of joints, and NV is going to be the number of joints plus the number of underactuated degrees of freedom, which is 6 for the humanoids and for all-legged robots typically. And then we have also the contact forces or the contact constraints, which are NF. So what we have is that we have NV plus NVA plus NF variables, because we have the accelerations, the torques, and the contact forces. So that's going to be around 70 for a humanoid. Then we have NV plus NF equality constraints, because we have the multi-body dynamics, which has NV lines. And we have the contact constraints, which are NF. And then we have also inequality constraints. So we're going to have inequality constraints on the accelerations, inequality constraints on the joint torques. And then we're going to have 4/3 NF inequality constraints for the friction cones, assuming we are using 4-sided pyramids, as I was showing you before. So the simplest version with just 4 sides for the pyramidal approximation of the friction cones. So we have 70 variables, 40 equality constraints, and here another bunch, roughly 70 inequality constraints. So that's the kind of problem we need to solve. So what about the computational cost of solving this problem? Well, in theory, the cost of solving a least square program should be dominated by the numerical decomposition of the Hessian matrix. So that's the matrix of the quadratic form of the cost function. So you're typically going to do a Cholesky decomposition, which has a complexity which is in the order of n cubed. So if we know the computation time for a certain number of variables, we know that every time we double the size of the problem, the computation time should become 8 times larger. That's what a cubic complexity means. Twice as many variables, 8 times more computation time. So can we solve this in 1 millisecond? And can we speed up the computation somehow by modifying the problem? And the answer is yes, we can. So the idea, which is actually behind much reformulation of numerical optimization problem, is to exploit the structure of the problem to make it faster to solve. So what kind of structure do we have? Well, if we take a look at the equality constraints, which are the dynamics and the contact constraints, we can see that there is a very specific structure in the matrix we have here. Can you spot it? Yeah, it's block lower triangular, because these are blocks, they are not single elements. So we have a bunch of zeros here. So we have a block lower triangular matrix. And also here, we have an identity matrix, which is important because identity matrices are very easy to invert, right? And so we can exploit this fact to simplify a bit the problem. So we can do like a pre-solve of this constraint by computing the variable corresponding to this identity matrix, which is tau, because the identity multiplies tau, and expressing tau as a function of the other decision variables of the problem. And that we can do it trivially because we have an identity matrix here. So tau is directly expressed as a function of v dot and f without computing any inversion. And that's the case only for tau. We couldn't do the same for v dot or for f. To express v dot as a function of the other variables, for instance, we need to invert the mass matrix M. And to compute f as a function of the others, again, we need to invert typically the Jacobian matrix, which is even more difficult because it's not a square matrix. So the only variables that we can easily eliminate from this problem is tau, because it's associated to an identity matrix in the constraints. And that's a trick that works in general. So if you have an optimization problem where the constraints have this structure, you can apply this trick. So we can represent our optimization variables, v dot, f, and tau, as a function of only the first two of this variable, v dot and f. Because the third one, tau, is easily expressed as a linear function of the other two variables without doing any matrix inversion. So we get this reduction in the number of variables basically for free, because we don't need to do any complex computation beforehand. So we have the new problem variables, which is y bar. And then we can just take the problem as it was formulated before and replace y with this expression, which depends on y bar. And y bar becomes our new decision variable for the problem. Agreed? Okay, so this is our original problem. And then we use this expression, so y as a linear function of y bar, to reformulate it under this form here. So the advantage is that not only we have less decision variables, but we also reduced the number of constraints. Because now the last row of the constraints, this one, can be removed. Because that's the row that we used to express tau as a function of the other variables. So it makes no sense to maintain that constraint because it's automatically satisfied by definition, because we already used it. So we have less variables and less constraints. So it's a win-win situation. So in theory, we could try to improve even more. There are tricks that can be used to make this problem even more efficient. So for instance, if you have a floating-based robot, we could remove the first 6 variables of v dot, exploiting the structure of the first 6 columns of mu, which are very easy to invert. We could also remove some or all the first variables by projecting the dynamics in the null space of J. So there are all these tricks which were very popular around 2010, 2015, in those years, which were actually the years when I was doing my PhD. And so I am very knowledgeable on all these little tricks. But in hindsight, I don't think they are very useful because you need to do a lot of work in coding your problem to exploit this trick and make them effective. And it's not really necessary in practice. So I think that once you have done the first trick of removing the joint torques from the decision variables, that gives you probably 90% of the benefits that you can get applying all the tricks in the book. And so that's the only one that is worth implementing in practice. Okay, one final piece of information before we finish with the theoretical part. So far, I've always assumed that we were working with an Euclidean space task function. So y, the output function that we use to generalize from end effector to task space control, we always assume that that was belonging to Rm, so an Euclidean space of size m. However, in practice, in robotics, we often want to control things such as the orientation of a body in space. And that does not belong to an Euclidean space. We already discussed it. That belongs to a Lie group. So you need to use things such as the quaternion or a rotation matrix to represent it. You cannot just represent it with a three-dimensional vector. Otherwise, you have the problems of singularities. So how do we deal with that? Well, we just need to make some tiny adjustments here and there. The main one is that assume that you're representing this variable y using a homogeneous matrix. So the homogeneous matrix, in case you don't know it, they are those matrices H, which have this structure. We have the rotation matrix, a position vector. Here you have a three-dimensional 0 vector, and here you have a 1. So R is the rotation matrix, which belongs to R3 times 3. And P is just a three-dimensional vector representing the position of a frame. Okay, so if you're using that representation, which is very practical, then to compute the error, of course, you cannot simply compute the difference between two of these matrices and imagine that you get something meaningful. You don't if you do that. So what you need to do is you need to compute the error in terms of the inverse of the first matrix times the second one. That gives you the relative rotor translation from the first frame to the second frame, which is a measurement of the error between these two frames. And then to transform this into an error vector, which is going to be a six-dimensional vector containing like a linear velocity in the first three elements and an angular velocity in the second three elements, you can use the inverse of the exponential mapping, which is the logarithmic mapping. Okay, so you can use this log function, which works on homogeneous matrices and takes a 4x4 homogeneous matrix and returns a six-dimensional vector, which corresponds to that matrix. Okay, so of course the linear part is trivial to imagine what it does. For the angular part, what you're doing is basically mapping the rotation matrix to its corresponding rotation axis and rotation angle, and that gives you an angular velocity, multiplying the rotation axis times the rotation angle. Okay, at least that's how I think about it. Okay, we don't need to implement this this function here, log, because it's already implemented in Pinocchio. If you want, you can go and take a look, but it's the inverse of the metric exponential, basically. So if you know what the metric exponential is, this is just the inverse operator. And if you don't know what the metric exponential is, well, it's just an extension of the standard exponential to matrices. So it's defined as an infinite summation over powers of the matrix. And again, Wikipedia is very good for refreshing your memory in case you don't remember. Okay, so these are just a bunch of references, and with this we are done with the theory. So now we should move to the implementation part. But before we start coding, I'm going to give you an overview of what the code is going to look like, so that you are not completely lost when we start working with the code. Let's start talking about how we implement task space inverse dynamics for a joint space problem. So we start simple to get acquainted with the code, and then we extend this to the task space formulation. So for implementing task space inverse dynamics, we're going to use a library, which is called TSID. It's a C++ library because we needed something to be efficient, and C++ allows you to write code that is very efficient. But to make things a bit simpler for your development, actually this library comes with Python bindings. So we're going to use it from Python. So we have the efficiency of C++, but we have the user flexibility of Python for writing the code, which makes it much, much nicer. So TSID relies on the library eigen for doing linear algebra computation, which you might have heard is very famous. We rely on Pinocchio for doing multi-body dynamics computation, and we rely on quadprog for solving quadratic programs. Actually, the problem we are solving are least square programs, but we saw that least square programs are just a special case of quadratic programs. So we can use a QP solver to solve a least square program. That's not a problem. So this library is completely open source, and you can find it on GitHub at this page. So just before starting to use this library, why did I choose to use it? Well, this library, as every library, comes with some pros and cons. The main cons, in my opinion, are that some features are still missing from this library, such as the possibility of using strict hierarchies between tasks, as I was mentioning before, is not implemented, even though it's in the API. Bilateral contacts are not there, even though I think that this year somebody implemented them, so I should update this. And line contact, so if you have a contact, if your robot has a sort of a line foot, which is neither a point nor a surface, you have a very narrow, long foot that's not available in the library. But of course, things can be added, such as the bilateral contact, which I think this year were added. So regarding the pros, it's an efficient library because it can run for a humanoid robot in less than 0.6 milliseconds. I've tested it. It has been tested on both humanoids and quadruped robots. It is open source. The design is very modular, so it is done to be extended quite easily. It comes with Python binding. It's easy to install because there are Debian packages, so you can just do sudo apt install and you have it. And also very important, I don't know many alternatives to this library. There is just this one, which is called Orca, which has been developed in Paris by other researchers, but that also comes with pros and cons. And the main cons is that it doesn't have Python bindings as far as I know. So I don't think it's as good for this kind of teaching context. Okay, so now TSID has been running for 6 years. We have almost 600 commits, almost 100 issues, more than 100 pull requests, and 64 forks. So it's been quite active in these years, and there are a bunch of people. I've counted 25 contributors. I am the initial designer of the library, and Justin has been helping me a lot in the development. And then Guillaume is currently the main maintainer of the library, the one that is taking care of releasing the the Python bindings and all the binaries, the Debian packages. And then we have a bunch of people who have contributed, adding specific features that they needed along the years. Okay, so let's start seeing what are the main concepts inside the library so that you understand more or less what's going on when we start seeing the code. So the main concept, I would say, is the concept of a task, which is something we already introduced. A task is something you would like the robot to do. So a few examples are a joint posture task for controlling the posture, so the joint angles of the robot. A joint velocity limit task. So this is a task that is simply trying to make sure that the joint velocities don't exceed a certain value. So even inequality constraints are modeled as tasks. And joint torque limits could be another task. Then we have another class, which is called robot wrapper, which is the one that contains a representation of the robot model and gives you functions for computing the quantities we need to work with the robot. So the mass matrix, the Jacobian, the center of mass, whatever quantities that is related to the robot model, you can compute it through this class. And then you have the core class, which is called inverse dynamics formulation, which is the one where we collect together all the tasks that we want to the robot to carry out and transform this task into a least square optimization problem. Okay, so this is where we need to do all the job of converting this like robotics geometric problem into a numerical optimization problem, which we can then pass to a solver, and then the solver computes the solution. Okay. And then, of course, we have a class for representing a QP solver. Actually, you're always going to see this H in front of QP, so HQP. The H stands for hierarchical, and that comes from my design choice of having an API that allows for hierarchy of tasks, so strict priorities between the tasks. In practice, you can only have two priority levels. One is going to correspond to the constraints, and one is going to correspond to the cost function. If you try to introduce a third level of priority, you're going to get an exception. Okay, so it's a fake hierarchical solver. Maybe when I retire, I will implement the hierarchy. So let's go a bit into the details of how you implement this and the API of the library. So these are the main methods of the robot wrapper class. The robot wrapper takes as input a URDF file. URDF stands for Universal Robot Description Format, or unified, I don't remember. Anyway, it's a sort of XML format that allows you to represent a robot model with all the geometric and dynamic parameters. And then you need to specify the kind of robot you're working with, so the kind of root joint. So this is there to distinguish between the case of a fixed robot, which is attached to the ground, so the root joint is fixed, or a mobile robot where the base link is free to move in space. So if you're going to have a legged robot, here you need to specify that the root joint is mobile. If you have a fixed robot, well, you can just not specify anything. I think that by default, it assumes the robot is fixed. Then you have methods to get the size of the configuration vector Q and the velocity vector V. And remember that for a legged robot, these are not equal because NQ is going to be 1 larger than NV. Okay, here we can recover a reference to the robot model. You have this, I would say, handy method for computing all the terms that you need for performing robot simulation. So it computes them as the mass matrix, the bias forces, the Jacobians, all this kind of stuff. And then you have method for retrieving these elements of the mass matrix, and the bias forces are called nonlinear effects here. So this is the vector H. It has a different name in the codes than what I used in the slides. Sorry about that. Then there is the central class inverse dynamics formulation, which has methods for adding task to the problem. And actually, we have three different methods. One is called add motion task. And this is to be used when your task depends on the joint accelerations. So that's going to be the case for most tasks, because you typically are defining tasks that depend on the motion of the robot. So when you add a task, you need to specify a weight for that task. That's the weight that's going to be using the cost function for summing all the task functions. And you need to specify also a priority. So as I told you before, the priority can be only one of two values, either 0 or 1. If I remember correctly, but I could be wrong, priority 0 is for the constraints, and priority 1 is for the cost. So the task could be either modeled as constraints, so they need to be satisfied exactly, or they could be modeled as costs, so they need to be satisfied in the least square sense by minimizing the error as much as possible. Then you have a method for transforming the problem as you formulated it by introducing task into a QP problem, basically. And that comes in the form of this HQP data. So HQP data, if you go and take a look at how it is defined, is just a vector of constraint level, where each constraint level is just a vector of pairs containing a double and a constraint. So the double is going to be the weight associated to the task, and this constraint is just basically a matrix and a vector, which could represent a constraint which is either equality constraint, AX equal B, or an inequality constraint, AX less than or equal to B. So it contains the matrix A, the vector B, and the fact of whether it is equality or inequality. So HQP solvers, we have a bunch of HQP solvers that are implemented, but they all implement the same interface, which is basically these two methods, a method for resizing the problem. So this, you typically call it only once before you start controlling the system, because you need to decide what is the size of the problem. And this does all the memory allocation. So it's better if you use this before you start running your controller, because this could take a lot of time. And then you have a method for solving the problem, which does not allocate any memory, because all the memory allocation has been done before. It's very important when you do embedded optimization to take care of the memory allocation before you start running the codes, because that part has a non-predictable time, because the memory that you allocate is basically asked to the operative system, and you cannot know how much time the OS is going to take before giving you the memory that you asked for. Okay, so even if most of the time it's going to be very fast, the one time you're going to run it on the robot, it might be much, much slower, and it could become a problem. So you typically do all the memory allocation beforehand, so that when you're running things online, you don't need to allocate any memory if you implemented things correctly, which is not easy. To do C++ implementation without allocating memory is quite challenging, but doable. So once you solve a QP problem, what you get back is a HQP output object, which contains a flag. the flag simply tells you whether the problem was solved successfully or whether it encountered problems such as maybe unfeasibility, unboundedness, or iteration limit reached. And then you have the vector of the optimal value of the decision variables, x, and the vector of the optimal value of the dual variables, the Lagrange multipliers, lambda. This typically you don't need it, but it's there. So we have several solvers implemented. None of them supports the hierarchy. So we can have only two hierarchy levels. All the solvers we have implemented are based on this a-quad-prog, which work with eigen for doing the linear algebra operations. We have implemented two optimized versions of the basic solver. One is called a-quad-prog real time, which is the fastest, but you need to know the matrix sizes at compile time because it pre-allocates everything at compile time. So I think this cannot be used from Python, I think, not sure. And then you have a-quad-prog fast, which work with dynamic matrix sizes, so you can change the size of the problem after you create the solver, but it's slightly slower. Still pretty fast. So I did some profiling 6 years ago on a very old computer of this HRP2 robots, which I was using at the time. And you can see that even for the slowest solver, which was the basic a-quad-prog, on average, this TSID problem was solved in less than 1 millisecond, so 0.7 milliseconds. And even if you take the worst case performance, we are still below 1 millisecond. And that was a humanoid robot, so we had like 60 variables. If you do that on a manipulator or on a quadruped, it's going to be faster because you have less degrees of freedom of the robot. Okay, so that's it for the overview of the code. We can now start coding. So if you have the org repository downloaded on your machine, then you should go to this folder, reactive control/TSID. Inside that folder, you will find this script here, and this is our starting point for coding. So this implements a simple controller for a robot manipulator, a UR5 robot, which is the same one we have upstairs over there in the lab. And we can start taking a look at that. So if you have some trouble with the setup of your machine, I think now it's a good time for me to help you a bit with that. In the meantime, I'm gonna open Visual Studio Code and show you the file. So this is the file you should have opened.
I don't know if yours is clear. I might as well face down. Veramente sono si muove, non è. Non è un'idea.
Non è proprio mobile.
No.
E dentro l'unica cosa che si usi quel comando di base non hai la shell folder. Quindi devi uscire, fare l'exit, e rifai quel comando, però te lo aggiungi prima di andare a fare aggiungi un B spazio, e poi vai qui dove si fa il sharing local host. Allora, devi mettere prima la directory sulla tua macchina, devi sapere qual è la directory dove hai lanciato, dove hai scaricato il codice di York, e poi qui ci metti la directory sulla macchina Docker, che va bene, puoi lasciare quella. Devi fare il git pull della repo Octi che lo trovi sotto. Git clone, fai quel comando lì, così ti scarica la directory Octi. Sì, ma non andrà poi, quello dobbiamo ancora integrare. A voi serve una mano con il setup?
Non dovrebbe, se va example.py dovrebbe essere a posto, giusto?
Test software.
Sì, non so cosa. Sì, test software. Sì.
Se vi va quello, a posto. Avete provato anche il viewer?
Quello. Questo qua, e poi c'è questo qua. Vabbè, adesso che lo chiudo, c'è i grafici su X.
Sì, esatto. Se vedete i grafici, vedete il viewer, siete a cavallo.
Qual è il test? Dovrebbe andare.
Test software.
Bravo.
Ok. Allora possiamo iniziare a guardare il codice se siete tutti operativi. Okay, so this is the code X0 UR5 joint space control. Let's take a quick look at what it does. So we first load the URDF file of the robot, and then we create a robot wrapper. Then we create another robot wrapper, but this is not the same one. It's a very similar robot wrapper, but this one is the one that is used inside TSID, whereas the second one is the one we are gonna use for doing simulation, because they can be used also for doing simulation. I could use also the same one, but I think it's cleaner if I separate these two. Then I create an object of class inverse dynamics formulation at force. So this long name comes from the fact that when we formulate the inverse dynamics problem, we could decide which variables we use as decision variables. The standard way is to use acceleration, force, and torques, which is the one we have used for most of the class. But I showed you just 1 hour ago that it's better to remove the torques so that we get a problem which has less variables and less constraints. So we are left only with acceleration and forces as decision variables. So that's why we have ax force in the name, because we acceleration and forces as decision variable. Then we initialize the state of the robot with a certain configuration Q0, which is specified in the configuration file, and a certain velocity V0, which is just 0. Then we compute the problem data for the first time step, so time 0, state Q0 V0. This is just for initializing all the internal variables of the object. And then we start creating the tasks. So the first task we create is simply a task joint posture, which is the one that controls the joint angles of the robot. So we're controlling all the robot in joint space. Very simple. After we create the task, we need to specify the gains. So we have the proportional gain Kp, the derivative gain Kd. The value of these gains is specified in the configuration file. So we have this Kp posture, which is a scalar that we need to multiply times a vector of 1 so that we get a vector of NV values, 1 for each joint. But we are setting all the gains for all the joints to the same value. The derivative gains, I typically don't ask the user to specify them because I simply set them to 2 times the square root of the proportional gain. And this is a very common strategy to get a system that is critically damped. So you get to the reference as fast as possible without overshooting. It's typically a good strategy. And then we can add this task using the add motion task method, specifying the weight of this task, the priority, which is 1. So 1 means this task is going to go in the cost function. 0 would have meant it goes in the constraints. And then we have this 0, which is the transition time in case you want to introduce a task smoothly while the robot is already controlled. But since we are in the initial setting phase, we don't need any smoothing. So we set the transition time to 0. Then we create a reference trajectory for the task to follow. This is actually a very trivial reference trajectory because it's a trajectory which is constant. So this is trajectory Euclidean constant, and we specify which is the constant value we want to control, which is Q0. And we get this traj posture, which we can set as a reference for the postural task. So if we want the postural task to track another kind of trajectory, we need to use this method set reference to modify the reference that is tracked by this task. We are typically going to use sinusoidal references. I'm going to see in a moment. Then we create another task here, which is this task joint bounds, which specifies velocity limits. So we set a minimum and a maximum velocity for all the joints, and we add that task to the soup. In this case, you can see that the priority is 0, which means that this task is going to go in the constraints, not in the cost, which makes sense because it represents inequality constraints. Then we create a QP solver.
How does it differ from equality constraint and inequality constraint? So
that's already embedded inside the task definition.
Okay.
So all the tasks that are bounds, they are inequality constraints. So it's written basically in the name. And inside the library, we specify which task is a inequality and which one is a equality. This will become more clear when we go more in the next pack of slides. So we create a solver and we resize the problem, specifying the number of variables, the number of equality constraints, and the number of inequality constraints, which is automatically computed by the formulation object. So every time we add a motion task inside the formulation object, it updates the number of equality and inequality constraints. The number of variables is constant because that depends only on the robot model. Okay, then we decide for how many time steps we're going to run the simulation. Is this capital N variable? We pre-allocate variables for containing all these quantities, so the joint torques, the joint angles, the joint velocities, the joint accelerations, the reference joint angle, velocity, and accelerations, the desired joint accelerations, and we just get a sample of the posture from the trajectory, which is a constant, so it's going to be the usual constant value. However, we don't want to track really a constant value. We want to track a sinusoidal trajectory. So here we decide the amplitude, the phase, and the frequency of the sinusoidal trajectory, which are specified in the configuration file. Then we initialize the time to 0, the time step dt, the initial state of the system Q and V. And then we start a for loop which does the simulation. So in the for loop, our main job is to compute the reference trajectory, which we compute as a sine summed to the initial configuration of the robot Q0. So we're going to track a sinusoidal movement around the initial configuration. And we need to compute also the derivative of this reference trajectory, so that we not only have qref, but also we have vref and dvref. So here I just computed the derivatives analytically. I know that the derivative of the sine is the cosine, and the derivative of the cosine is minus the sine. There's nothing complicated here. Then once I have these values, I set them as my values inside my sample posture object, which I set then as a reference in the posture task. Okay. So here the API, I think, has room for improvement. It will be maybe easier to simply pass these three values to the set reference, but it works like that. The set reference need to take an object of this class, like sample posture, and inside sample posture we need to specify the value for the position, for the velocity, and for the acceleration using these three methods: value, first derivative, and second derivative. Okay, so once we have the reference trajectory set, we can simply call this compute problem data, specifying the current state of the robot, Q and V. This you can get them from sensor or state estimation. And what you get is a HQP data object, which is a representation of a QP problem, basically. And then you pass this HQP data to the solver through the solve method. And what you get is the solution. So the solution contains the status flag, which you can check. It should be 0. If it's not 0, it means that the QP problem has not been solved. So you should always have this check. If solve.status different from 0, then there's been an error, so you just stop everything. Otherwise, you can keep going and you can extract from the solution of the QP problem the joint torques using this method get actuator forces, and the joint accelerations using the method get accelerations. I'm also logging the desired accelerations that are computed internally by the posture task so that we can plot them at the end. These are not really needed. And then I'm using the joint torques tau, which are my motor commands, to simulate the robot for one time step. So I pass the joint torques to the simulator, and I specify the time step for which I want to simulate, dt. And after that, I simply log in my variables q and v the current state of the simulator, simu.q and simu.v. I increase the time. I update the viewer to show me the current state of the robot in the viewer. And then I measure how much time has passed. And if the loop has been too fast, I sleep for the time remaining so that the simulation runs in real time. Of course, if the computation is too slow, I cannot make it real time. It's going to be slower. But I'm just making sure it's not too fast. Okay, that's it. After that, we just have some plots. We are plotting the joint positions, the joint velocity, the joint accelerations, and the joint torques. So this is as simple as it gets. This is really the starting point for using this library. We can take a look also at the configuration file, which we have been using, which is this one. This is just a collection of all the configuration parameters of the previous file. So here we have the duration of the simulation in number of time steps, which is 2000. The duration of the time step, which is 2 milliseconds. So in total, we're going to simulate for 4 seconds. The starting configuration of the robot, which is a vector of 6 elements. Then we have the amplitude, the phase, and the frequency of the reference trajectory. you can see we're gonna have an amplitude which is non-zero only for the first 3 joints. For the last 3, the amplitude is 0, so basically we are not moving them. And then we have weights for the different tasks. We also have a weight for the end effector task, but we have no end effector task in this script, so this is not used. A weight for the poster task, which is useless because we have only the poster task, so weights are not useful if you have only one task. And we'll wait for the bounds, which again are not really useful because the constraints are exactly satisfied, so it doesn't matter how much we weight them. Then we have the gain for the postural task, which is 1. That's a pretty low gain. So we may come back here later to execute this, to change this. And then we have a couple of scaling factors for scaling the limits of the joint velocities and the joint torques. This is just to make the limits a bit stricter so that we can see the robot hitting the limits, otherwise it wouldn't hit them. And below you can see just a bunch of other configuration parameters for the simulator, which are not very interesting. You just have this use viewer, which you can set to false in case you don't want to use the viewer. Okay. So I'm already inside the correct folder and I'm using the Docker image. So I can directly run this. So Python 3, x0, ur5, joint space control.py. Okay. So when you run this, you should also open the Meshcat viewer inside your browser. You can use the browser in your host machine. You don't need to open the browser inside Docker. And you should see this robot manipulator, which is moving somehow. And at the end, you should see 4 plots appearing, which we're going to analyze one by one. Okay, so this is the plot of the joint angles. You can see that for the last 3 joints, the reference trajectory is constant, so there is no motion. And you can see that the joint remains very close to the reference because the scale here is 10 to the minus 17. So basically there is no motion. For the first 3 joints, instead, we have these sinusoidal references. And we can see that it takes a while to converge towards the reference. Actually, it doesn't really converge to the reference in 4 seconds. It kind of does for joint number 1 and 2, but it doesn't for joint 0. We can see that it's getting there. It's getting closer and closer, but it has not converged in 4 seconds. We can also take a look at the joint velocities. In the joint velocity plot, we also have the joint velocity limits. We can see them here. There are these dotted lines, red for the upper bound and green for the lower bound. And we can see, especially for the first joint, can zoom in a bit here. We can see that the joint reached the velocity limit here. So there was a saturation of the velocity at the lower bound. And probably this is the reason why this joint took so long to converge, much longer than the others, because reaching the limits prevented it from tracking the trajectory. Here we can see the joint accelerations. This is also interesting, especially for joint 0. If we zoom in a bit here on joint 0, we can see that we have 3 plots, 3 trajectories. One is the real acceleration, q double dot. One is the reference acceleration, q double dot ref, and these are the same that we also saw for the positions and the velocities. But here we have also a third line, which is q double dot desired. So Q double dot desired, if you remember from the slides, was the acceleration that we basically asked the robot to generate. It's the one that we use in the cost function. So the cost function in this problem is Q double dot desired minus Q double dot to the in norm to the power of 2. So the solver is trying to make Q double dot equal to Q double dot desire while satisfying the constraints. So indeed, we can see that for most of the time, Q double dot, which is the blue line, and Q double dot desired, which is the green dotted line, are overimposed. Those are equal. Except for a few moments here, where we can see that Q double dot desire continues on the same path, whereas the real Q double dot jumps from this value to 0, and it stays at 0 until Q double dot desire becomes positive. So here, can anybody who has not seen this before guess what happens? So I'm mainly asking the two of you because the others have already seen this in class. Do you confirm, Matteo?
Yeah.
Do you remember?
Yes, yes.
Okay. Why would the acceleration become 0 instead of being negative at that point? Because the solver, by doing that, it's paying a higher cost. So it wouldn't do that if it was possible to have Q double dot equal to Q double dot desire. So why would it not choose a value that results in a lower cost?
You are hitting a bound.
Which bound? I think we only have one inequality constraint in this problem, which was the joint velocity limits. So the reason is that we are hitting the joint velocity limit. Indeed, that's what we saw 1 minute ago when we were looking at the joint velocity plot. We saw that joint 0 was saturating the velocity at the lower bound. So if your velocity is at the lower bound and you apply a negative acceleration, well, you're going to violate the velocity lower bound. So what you have to do when your velocity is at the lower bound is setting your acceleration to 0, because that's the lowest acceleration that you can afford. So it becomes 0 and it stays at 0 until the desired acceleration becomes positive again, and then it can track it. Okay. And this happens also here, but with the opposite sign. So here probably, well, not probably, here surely the joint was hitting the upper velocity bound, and so the acceleration had to go from a positive value to 0. And here we can see instead the joint torques. But since I haven't included torque limits, it's not super interesting. We can take a look at the torque profiles anyway, because we can see that there is something going on here. Always on joint 0. So we can see that the torque profile is mostly continuous, except in a few spots, like this region here, we have clearly a jump. And also here we have a jump, a discontinuity. And if you compare this plot to the previous one, you can see that these jumps in the torque profile corresponds to the moment where you had the jump in the acceleration profile, which makes sense because torque and acceleration are related linearly. So if one jumps, also the other jumps. What's maybe not so obvious is that this jump in the acceleration of joint 0 result in discontinuities in the torque, not only of joint 0, but also joint 1 and joint 4. And this is because we have the so-called dynamic coupling between the joints. So the acceleration at one joint is the result of the torque at all the joints of the chain, not only the torque at that specific joint. And mathematically, this comes from the fact that the mass matrix is not a diagonal matrix. It has also off-diagonal terms. So we have this relationship between torque and acceleration at all the different joints of the robot. Of course, if you actually plot this matrix, you're going to see that some elements are very large and other elements are very small, because there are some joints which are almost decoupled. And indeed, we can see that the effects of this jump in joint 0 is not equally distributed across all the joints. So on joint 2, 3, and 5, we can barely see any jump. So this suggests that joint 0 is dynamically almost decoupled from joint 2, 3, and 5, whereas it has dynamic coupling with joint 1 and 4.
I don't get the why tau 0 doesn't go to 0, but is positive when the acceleration instead goes to 0.
Mainly because of gravity. So to get a 0 acceleration, you need to compensate for gravity. So probably this is something like the gravity compensation torque.
Okay.
You might also have some Coriolis and centrifugal effects that you need to compensate for, but typically gravity is dominating. Okay, so what we can do now is we can try to make the robot converge a bit faster by adding, by increasing the proportional gain of the posture task. So by default, you had a postural gain of 1. We could make it equal to 10, for instance. You have to go in the configuration file, which is called x0ur5conf. You can make this gain equal to 10. And we can try to run again the script. So every time you rerun the script, you need to refresh the page of the browser where you're showing the viewer. Otherwise, it doesn't work. But in this case, visualizing the robot is not very interesting because it's doing this randomic movement. Okay, now that we used a higher gain, we can see that the convergence of joint 0 happens much faster. Also for the other joints, it happens faster, but especially for joint 0, which was taking forever to converge. What's fun is that now we are not even, well, we are still hitting the limit of the joint velocity, but not at the first valley, let's say, of the reference, but we are hitting it here at the second peak of the reference. So we can expect that here we're going to have a discontinuity in the joint acceleration. It's roughly around 1 second. And indeed, here at 1 second, we can see that we have the discontinuity in the acceleration. And here we have the joint torques. Again, discontinuity here. Okay. I don't think there is much more we can do with the script because it's so basic that it doesn't allow us to really change much. I mean, we could change the reference trajectory. We could increase the frequency or increase the amplitude, whatever, but I don't think it's super interesting. I think it's better that we move on to something more complicated. So maybe since we have been going on for 1 hour and a half, we take a break before we pass to the task space control. So it's 10:45. Let's see you back here at 10:55. Okay, so let's go back to the slides and see an overview of how we can move forward and extend the joint space control to a task space control. So far, we have only seen motion task. So tasks that depended on the joint accelerations, because we have seen the joint posture task and the joint velocity bound. However, we can also have tasks that depend on the other variables of the problem, which are the contact forces, if we have contact constraints, and the joint torque, so actuation. And another concept that we're going to introduce right now is the concept of rigid contact, which we have seen in the theory, but it's also something that is represented inside the TSID library as its own class. So there is a class called rigid contact, which is in many senses similar to the concept of a task, because we know that the rigid contact introduces a constraint, which is kind of like a task. I mean, it's telling you that your acceleration needs to satisfy certain constraints. But the main difference is that when we introduce a rigid contact, we are also adding variables to the problem because we introduce some force variables, which becomes then decision variables for the LSP problem. And of course, now that we have introduced rigid contact, we can also say that the inverse dynamics formulation class, which we have already used, can not only collect the tasks, but it can also collect rigid contacts. And it translates everything into a HQP. Okay, another concept that you can find inside the class, and it's useful to understand a bit better how this library works inside, is the concept of constraint. We have actually already seen that when we saw how a HQP problem is represented. It was basically represented as a vector of constraints. So what is a constraint? It's a purely mathematical concept. It has nothing to do with the robot model. It's just a way we use to represent a HQP program. And it defines an affine function. Well, the robot wrapper, we have already seen it. The trajectory, we have already used it in the script, which is just a mapping from time to vector values. It contains position, velocity, and acceleration. And we haven't used it yet, but when we will move to the control of the end effector, we will see that there are also trajectories where position and velocity have different sizes, because on the position we have the quaternion, and on the velocity we have the angular velocity, so we have size 7 for position and 6 for the velocities. So let's see a bit more in detail what's inside this constraint object. We have three kinds of constraints. We have equality constraints, which represent constraints of the kind AX equal small a. We have inequalities, which are stored in this format. So we have a matrix A, which pre-multiplies X, and then we have two vectors, one representing the lower bound, one representing the upper bound for that quantity. And then we have simple bounds, where we are just bounding the decision variables X. Okay. The reason why we have both these, because of course, this is only a special case of the first one, where the matrix A is the identity, is that some solvers allow you to specify simple bounds directly, and they have a specific method to deal with simple bounds that is more efficient than the methods they use to deal with more general inequality constraints. And so if you have such a solver, it's good that you can differentiate between this and this, so that the solver is faster, basically, just for computational reasons. Okay, so if you look at the API of this class constraint base, you will see that it has all these methods. You have these three methods to check if it is a equality, inequality, or a bound. So that basically answers your question from before. How do we know whether it is a equality or inequality? Well, there are these methods that the solver calls, and it figures out what kind of constraints the task represents. And then you have the method to recover the matrix, the vector, the lower bound, the upper bound, and also for setting these quantities. And you have a method for just evaluating the constraint to check whether it is verified or not at a specific point X. Then we can take a look also at the API of the task-based function, which is the mother class of all the task classes. So the interface is very simple. A task has just a name, which is a string. It takes the robot model as input. And at every control loop, we call the compute method on the task. I mean, we don't do it directly. It's done automatically when we call the compute method on the inverse dynamics formulation object. Internally, that calls the compute method on all the tasks that we added. And this method depends on the time, the robot configuration, the robot velocity, and this data object, which contains all the data of the robot model. And it computes basically the constraint. So it returns a constraint, which is going to be something like AX equal to B or AX less than or equal to something. We have three kinds of task. Task motion, which we have already seen, when your task depends on the joint accelerations. And then we have task contact force, when the task depends on the contact forces, and task actuation, when it depends on the joint torques. So here are some examples of tasks that result in equality constraints. We have task COM equality for controlling the center of mass of a robot. This will be very useful when controlling a walking robot, because the center of mass is a key quantity you want to control for walking, because it's the one that determines the balance of the robot. Task joint posture, we have already seen it. And task SE3 equality is for controlling the position and orientation of any body of the robot. So typically the hands or the feet of the robot. Then we have tasks that are bound, such as task joint bounds, which we have already seen for the joint velocity limits. And then we have tasks that are inequality constraints, such as the friction cones for the contact forces. Those are not simple bounds, they are inequality constraints. So this is instead the interface for the contact class. This is the most complex part of the library, the modeling of the contacts. So each contact has a name. You have a couple of feedback gains that are used just for regularizing the contact constraints. I'm going to give you a bit more detail in a moment. We need to specify what's the name of the body which is in contact. So typically that's going to be the name of the foot. Each link in the robot has a name that's specified in the URDF file. So you can just look the name of the links there and use that name here. And you can specify also a regularization weight that's going to be used for regularizing the contact forces in the cost function. Again, I will explain more clearly in a moment. Then you have 4 different methods. One for computing the motion task, one for computing the force task, one for computing the force regularization task, and one for computing the force generator matrix. So every time we add a contact, we are adding actually a lot of things inside the problem. And here we need to go a bit further what we have seen in the theory, because the theory doesn't worry about numerical issues, whereas when we do the implementation, we need to worry about numerical issues. So let's take these 4 methods one by one, and let's describe what they do. So first one, compute motion task. This is easy because we have already seen this when covering the theory. So this represents the motion constraints caused by rigid contact. So this says something like jv dot equal minus j dot v. So the contact point accelerations should be 0. And we know when we create a contact, we need to add that constraint inside the QP problem. So this is a method that does that computation for us. However, especially if you're working in simulation, you may want to add some stabilization term to this task, because otherwise you might get a drift in the position of the contact if you're simply taking the acceleration that are coming out of the QP and you're integrating them. So this is not needed when you're working on a real robot, unless you're afraid that the contact might slip away. In that case, it's useful to have them. But if you're sure that the contacts are not slipping, like if you have a humanoid that is standing on both feet, that's very difficult to make the feet slip. In that case, you don't need them on a real system. So this is mainly for doing simulation. And these 2 gains, Kp and Kd, are these gains here that you specify in the constructor. Then the second method, compute force task, is the one that computes the friction cone inequality constraints. So again, this is something that we saw already. You just compute the matrix and the vector to represent the inequality constraints on the contact forces. So of course, these are going to represent the friction cone constraints if you have a unilateral contact. You might also have bilateral contacts, which are contacts where you are really attaching to points of the robot, which are useful for modeling closed kinematic loops. If your robot has a closed kinematic chain, the way you model it is by introducing a contact that is bilateral. So you can both push and pull on that contact. In that case, you don't need this. So you're going to specify that there is no inequality constraint on the contact forces. So those are the first 2. Then we have the third method, compute force regularization task, which is something we didn't cover before. This is mainly to make sure that the contact forces that are computed by the solver are not crazy large, which might happen in some situation. And also to keep the contact forces close to the center of the friction cones. Because just having the friction cone constraints is only ensuring that the contact forces are inside the friction cones, but it's not pushing the forces to be close to the middle of the friction cones, which would be better for robustness. So in order to encourage the solver to keep the contact forces as close as possible to the middle line of the friction cone, we have this force regularization task. And this regularization weight is basically deciding how much weight we want to give to this task. So typically this is going to be a very small value, like 10 to the minus 4, 10 to the minus 5, so that this doesn't get in the way of the higher priority task, such as tracking the center of mass trajectory, tracking the feet trajectories, this kind of more important task. Okay, last we have this method, compute force generator matrix. So this is a bit tricky because this is something that we didn't cover at all in the theory, and it's actually something that is never discussed even in the paper, in the literature. So I need really to explain it to you from scratch. So this force generator matrix is a matrix which we call T, which maps the force variable to the motion constraint representation and is introduced in the dynamics here. So it's a matrix that pre-multiplies the contact forces before the contact forces can be multiplied by the Jacobian transpose. And in theory, this matrix is not strictly necessary. Indeed, we didn't talk about this so far. However, in practice, it's very handy to have this matrix. Let me show you why with an example. So suppose you have a unilateral plane contact. So you have a foot, which is like a rectangular shape, and this foot is making contact with the ground. So this contact constraint has a dimension of 6, because your foot now cannot move in any direction and it cannot rotate about any axis. So you have 6 contact constraints, 3 for the position and 3 for the orientation. So what you could do is that you could represent also the corresponding contact forces with a 6-dimensional vector, which would contain a 3-dimensional force and a 3-dimensional moment. Okay, and that's how we thought about it so far. The problem is that the friction constraints on the 6-dimensional force are very hard to express. So for the linear part, it's easy because you have a 3-dimensional force. You just say this force should stay inside the friction cone. But what about the moment? Also, your moment is bounded because of the friction cone constraints. But it's very hard to express those constraints in terms of the 3-dimensional moment. So just to give you an example, if your moment becomes too large, then your foot is gonna tip over in one direction or the other. Or if your moment around the z-axis becomes too large, your foot may slip rotating about the z-axis. And you don't want that to happen. So you need to add some constraints on the moments, because you don't want neither to tip over nor to slip rotating. So in order to simplify the representation of the friction cone constraints, it's better not to represent the contact forces as a 6-dimensional vector, but it's better to represent the contact forces as a 12-dimensional vector, where you model it as a 3-dimensional force at each vertex of your rectangular foot. And those two representations are equivalent because you can always map from one to the other. But the advantage is that if you have 4 3-dimensional forces, now it becomes trivial to represent the friction cone constraints. So if we write the forces as a collection of 3-dimensional forces each one applied at the vertex, at one of the vertices of the contact surface, you get a redundant representation of the contact forces. But with this redundant representation, it's very easy to write down the friction constraints, because now they are simply three-dimensional forces. So we know how to write the friction constraint for a three-dimensional force. Okay. So in the classic case, we have a rectangular contact surface. Most robots have a rectangular foot. Then this results in 12 variables for representing the contact forces instead of 6. So we have a bit more variables, but it's easier to write the constraints. So it's a trade. Of course, we could use this redundant representation also in the motion constraints. We could say, instead of we have no motion and no rotation of this body, we have no motion for the 4 vertices of the contact surface. So we have 12 motion constraints. But the problem is that these 12 motion constraints would be redundant, because we have 12 instead of 6. And some solvers, such as the one we are using, don't work well when you have redundant equality constraints. Okay, so we cannot do that in practice. So we can use the redundant representation for the forces, and that simplifies our job of writing down the friction constraints. But we cannot use the redundant representation for the motion constraints, because the solver does not allow us to do that. So we need to maintain these 2 different representations. In the force space, we use the redundant one, which is 12-dimensional. But in the motion space, we use the minimal representation, which is 6-dimensional. And so we cannot then multiply the Jacobian transpose times the contact forces, because they have different sizes. The Jacobian transpose has a size of 6 in the number of columns, and the force vector has a size of 12. So their multiplication doesn't match. So to make this multiplication possible, we need to map the redundant forces, which are 12, to a minimal force representation, which is 6. And this force generator matrix allow us to do this mapping. So it maps the 12-dimensional force vector to a minimal representation 6-dimensional force. So we can then use it with the Jacobian transpose. Okay. And you can see how this was not really needed in theory, but in practice, when you need to implement stuff, you need to take into account what the solver allows you to do, and how easy it is to represent the friction constraints in different spaces, and all these details are needed when we want to implement stuff. Okay, so this is mainly to give you an understanding of what's going on inside the code. We don't need to implement this because that's already implemented in the library. But for using the library well, you need to know this kind of stuff, because otherwise you don't understand what these methods are, etc. Any question on that? Okay. So the inverse dynamics formulation class, it has 3 methods for adding new tasks. The first one, we have already used it, is for adding a motion task. And then we have other 2 methods, which are basically just the same API for adding force task or torque task, which I think now they're called actuation tasks, which is more general. Then we have a method for adding a rigid contact. Well, this one we have already seen it, a method for computing the HQP problem data, which is defined in this way, which we have already seen, but now we understand better what this constraint-based class is. And here I'm guiding you through one example. So let's consider a robot manipulator, but this time, instead of doing joint space control as we did before, we are going to do end effector control. And we also want to model the torque limits, which we didn't do before. The joint velocity limits, we already know how to do them. And that's one exercise, and then we move to the second one. Okay. So let's go to the code. And now we want to open X1 UR5 task space control. Okay, so this is the script we are working with. It's quite similar to the previous one. The main difference is that now we will add some extra task for modeling the torque limits and for controlling the position of the end effector instead of the joint angles. So actually now most of the setup for the TSID problem happens inside another class, which is called TSID manipulator. So we can open the file TSID manipulator and we can take a quick look at that. So most stuff here is the same as before. Let's only look at the different things. So one new part of the code is this task SC3 equality. So we need to specify the end effector frame name. So again, each body in your robot must have a name that's defined in the URDF file. And we know what the name of the end effector is, and we specify it here. So we set the proportional gain, we set the derivative gain as before. And we can also set a mask. So a mask works like that. We go to the configuration file, and here you can see the mask. So the mask in the case of an SE3 task is just a 6-dimensional vector containing only zeros and ones. The first 3 values correspond to the 3 translations, and the second 3 corresponds to the 3 rotation. So rotation about X, about Y, about Z. And we set 1 for the directions that we want to control, and zeros for the directions that we don't want to control. So in this case, we are controlling only the 3 translations. We are not controlling the orientation of the end effector. But if we wanted to, we could do exactly the opposite. We could control only the orientation and not the position, or we could control some directions in position, some direction in orientation. We can mix that however we want. And this is the name of the body we want to control, which is a fixed joint. Then use local frame false. This is to specify whether the control must happen in the local frame of the end effector or in the word frame, so a frame that is attached to the ground and fixed with respect to the environment. That's mainly useful when you're using a mask, which is a bit more complex. So in our case, the mask is only selecting the position part and not selecting the orientation part. But if you're using a mask that is selecting some directions, some specific directions, such as controlling only X, then this X can be the X in the local frame of the end effector, or it can be the X in the word frame. Typically, you want the X in the word frame because that is fixed, whereas the X in the end effector frame moves when the end effector moves. So you typically want to set this use local frame to false. And then we recover the ID of the end effector frame, and we store it there. And then we use this ID for computing the initial position of the end effector as a homogeneous matrix H. And we set this as the reference for the end effector trajectory. Then we add this task to the formulation. And then we create a task actuation bounds, which implements basically the torque limits. So we specify tau min, tau max, and we can be sure that the torque is going to remain inside these limits. And for the rest, there is nothing new. Everything else is the same as before. Okay, so after we have created the TSID problem formulation, basically this script is very similar to what we had before. We are just adding a couple of spheres in the viewer, we will see them later, to represent the reference end effector position and the real end effector position, so that we can visually see in the viewer how the tracking is going. And now the sinusoidal reference motion doesn't happen in joint space, but it happens in end effector space. And apart from that, everything is the same basically as before. So yeah, I don't think we need to comment this code. We can just run it and see how it behaves. So Python 3, x1, ur5, task space control .py. Let me open the viewer. You can see there are two bolts there. One is red, one is orange. Most of the time, they are overimposed because the tracking is good. So the bolts are on top of each other. It's just in the beginning that you have a significant tracking error, but it's very hard to see the robot in the beginning because you need to reposition the camera every time. And we can see that the script printed the average loop time while it was executing. So since I'm running this on Docker, it's quite slow, but it still takes only 1.6 milliseconds. So we are below the period of the control loop, which is 2 milliseconds in this case. So if you're running this on a native Ubuntu machine, I expect it should be faster.
0.3.
Yeah, that makes more sense. So yeah, it's 5 times faster. Yeah. On your machine, it's 1.2. You have some troubles on your machine.
Also for having was 1.2 in native Ubuntu.
Native Ubuntu. I don't know.
Initially 0.7 and 0.3. Then
well, the very first iteration, it can be very slow because you're setting up some variables, but this is due to the Python part of the code. Because here we are measuring both the Python part and the C++ part. So of course there could be some high variance, especially in the beginning, but on my machine after the first sprint, then it's quite consistent. It's always 1.6, 1.5, 1.7, and it never changes. And being on Docker, I think that time is reasonable. On a native Ubuntu, it should be around 0.3 as for Matteo. If it's not, I don't know what that means, but you installed with sudo apt install Debian packages.
I have 1.1 on Docker. So
yeah, so it's faster on your Docker than on her native Ubuntu machine. I don't know. Either you have a very slow CPU, but
so
it shouldn't. I don't know why, but yeah, shouldn't be that slow.
it's there for
You can complain to him. So here we see the tracking. That's the tracking of the end effector trajectory. We can see it's mostly good, at least in the X direction, but there are a few points in time where the tracking degrades. And these are not small errors, because you can see here the scale is millimeters. So this error is basically 1 centimeter, almost 1 centimeter. So something's going on here. Let's see if we figure out what it is. So what this is just the end effector velocity trajectory, but this doesn't tell us much. Let's take a look at the torque. So we can see that most of the times we are far away from the torque limits, but not for this joint. You can see that this joint here is actually hitting the torque limits a couple of times. And I think these two moments correspond also to the two moments where we had a degradation in the tracking of the end effector trajectory. So probably what's going on is that there are certain configurations for which we reach the torque limits for this joint. And so the controller basically cannot really provide the desired acceleration of the end effector. And we are also actually hitting the velocity limits quite a lot. Yeah, we're hitting them here, here, here in the beginning. Yeah, many, many times. So we're really performing at the limits of what the robot can do. This is a bit artificial, to be honest, because if you look at the configuration file, you will see that I have scaled the torque limits and the velocity limits by a factor of 0.4. So I'm considering limits that are 40% of the real limits of the platform. So we can try to make this more reasonable, maybe making that 0.9. And I expect that if I run that again with those higher limits, probably the tracking should be better. We're also getting very close to the singularity there because the robot is really stretching out to reach. Yeah, it's better. Because the scale now is different on Y. You can see this is basically 1 millimeter. So yeah, we have some slight deviations, but they're really tiny. So probably the degradation was due to the torque limits and the velocity limits. Now we can see that we never reach the torque limits. We still reach sometimes the velocity limits, like maybe here and surely there, but much less often than before. Let's see here if we reach them. Yeah. Yeah, we do reach them once at least, but overall the tracking is pretty good. So we can also try to make the life of the robot a bit harder by changing the amplitude of this trajectory. So right now we have an amplitude of 10 centimeters, so 0.1 in the x direction, and 10 centimeters also in the z direction. We can make this 20 centimeters. So it's probably going to be harder for the solver for the robot to track this trajectory. Let's see. Yeah, you can see that the red ball is going outside the workspace of the robot. So the robot really stretches out. It goes in singularity. You can see the typical oscillations that arise when you make the robot go in singularity with these kind of control methods. And we can see that the tracking is not really very good in the x direction. So the x direction is the one pointing forward towards with respect to the robot. So the robot cannot reach as far as we are asking it to go. And so it just go as close as possible to the reference. And this deterioration in the x direction actually results in an error also in the y direction. We can see also here in the velocity, it's pretty clear that we have these oscillations. They're much more visible in the velocities than in the positions, of course. They will be even more visible in the accelerations if we plotted the acceleration. Well, we plot the torques, which we know are linearly related to the accelerations, and we can see that they are super noisy. So this probably is not gonna work well on a real robot. Cannot really expect a real robot to do such a noisy torque profile. And these are the joint velocities, which are awful. But again, this is to be expected when the robot goes in singularity. So let's imagine we want to execute this on a real system. How can we make this more amenable to a real platform? Any suggestion? Decrease. Yeah, so right now it's 100. And try 10. Well, we did a pretty strong decrease, but it's just to take it to an extreme and see if we get what we expect. Seems better, less oscillation. But let's see the plots because the viewer sometimes can be misleading. Velocity profile of the end effector seems to be better. Also, the torques are better. And these are the joint velocities, which before they were pretty bad. Now they're much smoother. So this is something that could work on a real system. So yeah, decreasing the gain of the and the factor task worked. And that's a very general concept. If you're using a high gain, of course, you're going to track better. But when you start getting into trouble, such as close to singularity, close to the limits of the platform, having high gains can lead to very oscillatory behaviors, which, as long as you're doing a simulation, it's not a big deal, but on a real platform, they really don't work well at all. They can also then mess up your state estimation system, which then feeds back into the controller and makes things even worse. And maybe you start having really strong vibrations or even divergence. Okay. So we have a last, I think, yeah, last exercise to go through, which is X2 biped. So here we move from controlling a robot manipulator to controlling a biped robot. I had also some slides prepared for this, but maybe it's not. We can directly look at this stuff, I think, in the code. I'm just checking if there is something important that you need to see, but no. I think we can go directly into the code, so it's fine. Okay, so this is the code. Actually, the main script is kind of the same as it was before. The only difference is that now, instead of focusing on the end effector, we focus on the center of mass of the robot. Because when it comes to walking and balancing, your main focus should always be the center of mass. As long as the center of mass is above the feet, the robot can stay in static equilibrium. So you don't want the center of mass to go too far in front or behind or laterally outside the polygon containing the feet. All the formulation of the problem happens inside this other script, which is called TSID biped. So let me open that, TSID biped.py. It's always in the same folder. And here we can see how the problem is formulated. So most of it is going to be very similar to what we just saw for the manipulator. But here we have some new stuff, especially we have contacts, which we didn't have before for the manipulator. So contacts indeed are immediately created here. We can see that we create an object of this class contact 6D. 6D means that it's a contact that is constraining both the 3D position and the 3D orientation. So it's a typical plane-to-plane contact. That's opposed to the contact 3D, which is when you have a point-like contact surface. Like when you have a quadruped robot with points like feet, there you need to use a contact 3D. So we create a contact 6D, and when we do that, we need to specify the contact points. So the contact points here are specified as a matrix of size 3 times 4, because we have 4 contact points. Each one is a 3-dimensional point, so the matrix is 4 by 3. And here we are using the dimension of the foot of the robot to specify the 4 contact points, which are the vertices basically of the robot foot. Then we specify mu, which is the friction coefficient, which is in the configuration file. And we can also specify a minimum and a maximum for the normal force. So the normal force would, in theory, be allowed to be any positive value. But if we want, we could constrain this into a smaller range just for safety reasons. We don't want a too high contact force, but we also don't want a contact force that is too small, because otherwise we could break the contacts accidentally. So we always want to have at least maybe a couple of newtons of force on each contact point. And here we specify the direction of the normal to the ground, which is going to be just z, so 0, 0, 1. So we specify the feedback gains, Kp and Kd, which I explained you before what they mean. And that's it, basically. We set the reference for this task, which is the initial configuration of the foot. Then here we have this if statement, which chooses between these 2 ways of adding the contact. This is because we could add the contact motion constraints either as strict constraints or as penalties inside the cost. So that depends on the weight that we use in the configuration file. If we set a weight that is negative, then we're gonna do the standard thing of having the contact constraints as constraints. But if we want to relax the contact constraints, which can be useful to improve the feasibility of the problem, in case the problem becomes unfeasible, we can specify a weight that is greater than 0. And in that case, this is going to be added as a cost instead of a constraint. Okay. I think we don't need to do that for the bipeds. That's mainly useful for the quadruped robot, which has 4 contacts with the ground, and these tend to become redundant and to lead to infeasibility. With the bipeds, probably it's not needed. Then we do the same thing for the other foot, the left foot. So everything here is the same as before. Then we create a center of mass task with this object task COM equality. We set the gains, we add the task. We also have a task center of pressure equality. I don't think we are using this in this example. Let me check. Yeah, WCOP is set to 0. So let's forget for a moment about that. I will explain you what the center of pressure here is tomorrow. So let's just ignore this. Also, the angular momentum task is just for controlling the overall angular momentum of the robot. That can be useful for balancing, but I don't think we are using that. Yeah, we are using that, but it's a very low priority task with weight 10 to the minus 3. And then we have a joint posture task and task for controlling the position of the feet. In this case, actually, the feet are in fixed contact, so these tasks are useless, because since the feet cannot move, it's useless to have a task on the feet. But this is just a generic problem formulation that can be used later for walking. And when we need to walk, of course, we need to control the position of the feet. So this is just it's there, but it's for later. Then we have the torque limits, the joint velocity limits, and nothing more. This is just the references for the different tasks, COM, joints, and left foot, right foot. That's it. Okay, so we can take a look at the configuration file. Here we can see we have, as usual, the number of time steps, the duration of a time step. I've made this a bit larger, 5 milliseconds, so that we have a bit more time for computation. Actually, on Docker, I cannot run this in real time. It takes about 9 milliseconds to compute the problem. So it's going to be 2 times slower than real time on my machine. But then you can adapt this to your machine. If you need, you can make this large, or if you don't, you can make this small. When I was running this natively, it was below 1 millisecond. Then here we have the size of the foot of the robot in the X direction, positive and negative, and in the Y direction, positive and negative. The friction coefficient is set to 0.3. We have a 5 Newton of minimum force and 1,000 of maximum force. These are the name of the foot of the feet of the robot. The contact normal direction, which is simply Z, because the ground is horizontal in this example. And then we have the weight for all the tasks. So we can see that the higher weight is for the center of mass, which has a weight of 1. Then we have 10 to the minus 3 for the angular momentum, 10 to the minus 1 for the feet, which actually are useless because, as I told you here, we are not really controlling the feet, they cannot move. And then we have -1 for the contact. So -1, it means that we're gonna use strict constraints for the motion constraints. 10 to the -1 for the posture, and 10 to the -5 for the regularization of the contact forces. And then we have activated the joint torque bounds, but we have not activated the joint velocity bounds by default. So here we have a weird gain vector for the postural task, which we tuned by hand because we saw that it resulted in best performance. And then we have different scaling factors for the torque limits and velocity limits. And here we have the proportional gains of the different tasks, which are all set to 10, except the postural task, which is set to 1, but that's just because this just pre-multiplies this vector here. So it's tuned above. And that's it. There is nothing interesting going on there. So we can just run the script and see what it does. Open the viewer. Okay, there you have it. There is your humanoid robot, which is tracking a sinusoidal trajectory with the center of mass. Of course, the sinusoid is going left and right. You can see that the feet are not moving. The motion is not very smooth because I think I'm not updating the viewer frequently enough. I can change that. And go here and so the frequency of update of the viewer is this display N, which now is set to 20. I can probably set this to 4. So the viewer should update more frequently. And here I can see all my plots. So this is the tracking of the center of mass. And we can see it's not really tracking well. It's performing a movement which is in the right direction, but not with the amplitude that we are asking. These are, well, just the velocities of the same movement, and these are the accelerations. Any idea why it's not tracking well?
Because if we put the center of mass in that position, the robot will fall. So lose the contact of the feet.
That could be an option, but I don't think. I think that the weight of the center of mass task is not high enough. I think we can try to make this bigger. Maybe we set it to 10 and we try again. Let's see. It's hard to see from the viewer, but then we can see the plot at the end. The viewer at least now is a bit smoother than before. Yeah, we could probably also reduce the length 1010 steps. Looking at the values that are printed here, it seems that the tracking is quite good now, because the tracking error is always in the order of a few millimeters, whereas before it was in the order of centimeters. Yeah. So you can see with a higher weight, now the tracking is much better. Okay, so we run out of time. There are other things that I wanted to show you we could do with this script, but I think we can continue with that tomorrow. If you want to give it a try, the things that I wanted to try are actually written down in the slides that you have in the shared folder. So you can take a look and maybe give it a try on your own so that you can prepare when we do it in class. So see you tomorrow.